Right now, at this exact moment, while you're watching this video, the Earth is orbiting the Sun at nearly 30 kilometers every second. The Sun itself is racing around the center of the Milky Way at more than 800,000 kilometers per hour. Our entire galaxy, containing somewhere between 100 and 400 billion stars, is moving through the universe at more than 2 million kilometers per hour. On its own, none of that is surprising. Everything in space moves. Planets orbit stars. Stars orbit galaxies. Galaxies drift through an expanding universe. That's simply how gravity works. But hidden inside those motions is something astronomers never expected to find. Because the Milky Way isn't just moving randomly through space. It's moving towards something unimaginably massive, something powerful enough to pull not only our galaxy, but hundreds of thousands of others. And here's the strangest part. We can't actually see it. Imagine standing in the middle of a vast ocean. The water around you is perfectly calm. No waves, no wind, no storms. Then, without warning, your boat begins drifting. Slowly at first, then faster. You look in every direction. Nothing. No island. No ship. No visible current. Yet something is pulling you. Would you trust your eyes? Or would you trust the movement itself? This is exactly the dilemma astronomers faced. For decades, they believed they understood the large-scale motion of galaxies. The universe, according to the prevailing picture, was expanding uniformly. Every galaxy should move away from every other galaxy as space itself stretches. Imagine dots painted on the surface of a balloon. As a balloon inflates, every dot moves away from every other dot. No center, no preferred direction, just expansion. Elegant, simple, beautiful. It was one of the greatest discoveries of the 20th century. When Edwin Hubble observed distant galaxies in the 1920s, he found that nearly every one of them was moving away from us. The farther away a galaxy was, the faster it appeared to recede. This relationship became known as Hubble's law. It wasn't that galaxies were flying through space like bullets. Space itself was expanding. The universe had begun with the Big Bang, and ever since then, the fabric of space-time had been stretching in every direction. For decades, this picture explained almost everything astronomers observed. Galaxies drifted apart. Clusters slowly evolved. Gravity sculpted the universe while expansion carried everything farther away. Case closed, or so it seemed. Then astronomers built better telescopes, better detectors, better ways of measuring distance. And instead of confirming the simple picture, they discovered a mystery. Every galaxy possesses something called a peculiar velocity. It's an odd name, but the idea is surprisingly simple. Imagine you're standing on a moving walkway inside an airport. The walkway carries everyone forward at the same speed. That's like the expansion of the universe. Now, imagine one traveler decides to walk while standing on the walkway. Someone else walks backward. Another begins running. Even though everyone is still being carried forward by the moving floor, each person also has their own individual motion. Galaxies behave the same way. The expansion of the universe moves everything apart, but gravity adds an extra motion. Astronomers call this additional movement a galaxy's peculiar velocity. Normally, these extra motions are relatively small, a few hundred kilometers per second. Perfectly understandable. Galaxies tug on one another. Clusters interact. Gravity creates local disturbances. Nothing unusual. Then scientists measured the peculiar velocity of our own galaxy. And suddenly, nothing made sense anymore. The Milky Way wasn't simply drifting with cosmic expansion. It was racing sideways through the universe at nearly 600 kilometers every second. That's more than 2 million kilometers every hour. Far too fast to ignore. At first, researchers assumed the measurement was wrong. Scientific history is filled with false alarms. A calibration error, a faulty instrument, a mistaken calculation. Extraordinary claims require extraordinary evidence. So teams around the world repeated the observations. Again and again. Each new dataset told the same story. The Milky Way really was moving, and it wasn't alone. Nearby galaxies shared almost exactly the same motion. Then larger galaxy groups. Then entire galaxy clusters. One by one, astronomers realized something astonishing. It wasn't just our galaxy being pulled. Entire regions of the universe were drifting together. Imagine standing in a crowd where everyone suddenly begins walking toward the same invisible point. Not because someone told them to, not because they can see a destination, simply because something beyond the horizon is drawing them forward. That's what the universe seemed to be doing. The implications were enormous. Gravity strong enough to move hundreds of thousands of galaxies must come from something almost unimaginably massive. But where? To answer that question, scientists needed a reference point. Fortunately, the universe had already provided one. Nearly 14 billion years ago, the universe was unimaginably hot. Matter and radiation existed together in an opaque cosmic fog. Light couldn't travel freely. Every photon bounced endlessly between charged particles. Then, about 380,000 years after the Big Bang, temperatures finally dropped enough for electrons and protons to combine into neutral atoms. Suddenly, light was free. Those ancient photons have been traveling across the universe ever since. Today, we detect them as the cosmic microwave background. Think of it as the oldest light in existence. A photograph of the infant universe. What's remarkable about this ancient light is how uniform it is. No matter where astronomers looked, the temperature appeared almost identical. Almost. There was one subtle exception. One side of the sky appeared ever so slightly warmer. The opposite side appeared slightly cooler. Not because the universe itself was uneven, but because we were moving through it. It's the same effect you feel riding a motorcycle. The air in front feels compressed. The air behind stretches away. Astronomers realized the tiny temperature difference in the cosmic microwave background revealed our motion through space with extraordinary precision. It confirmed what other measurements had already suggested. Our entire local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller companions, was moving together. Not randomly, toward a specific direction. It was one of the most precise measurements ever made. Now came the obvious question. What was waiting in that direction? Researchers began mapping every galaxy they could find. They measured distances, masses, velocities. Cluster by cluster, they built a three-dimensional map of the nearby universe. At first, everything seemed promising. Large galaxy clusters appeared exactly where gravity predicted they should. Perhaps one of these giant structures explained the motion. But the numbers didn't add up. Nothing visible contained enough mass. Imagine finding footprints the size of a bus crossing a beach. You search for the animal that made them. You find birds, dogs, deer. Nothing remotely large enough to explain what you're seeing. The footprints are real, but whatever created them is missing. That's exactly how astronomers felt. The galaxies were leaving unmistakable gravitational footprints. Yet the source remained hidden. Then someone noticed something strange about the direction itself. It pointed almost directly behind the thickest part of our own galaxy. The Milky Way was getting in the way. Billions of stars, enormous clouds of gas, rivers of cosmic dust. Together, they formed an enormous curtain across the sky. Behind that curtain, Visible light simply couldn't pass. Astronomers gave this hidden region a surprisingly poetic name, the Zone of Avoidance. Not because the universe avoided us, but because for generations, astronomers had no choice but to avoid looking there. Imagine trying to discover a mountain range while living inside a dense forest. No matter where you stand, the trees block your view. The mountains are real. You just can't see them. For decades, that's exactly where the mystery remained, hidden behind our own galaxy. Invisible, untouchable, waiting. And what happened next would transform one of the greatest mysteries in modern astronomy into something even stranger. Because when scientists finally found a way to see through the Milky Way, they discovered they had only uncovered the first layer of a much larger story. For centuries, the Zone of Avoidance lived up to its name. No matter how powerful telescopes became, visible light simply couldn't penetrate the dense wall of stars and dust stretching across the plane of the Milky Way. To ancient astronomers, this glowing band across the sky was beautiful. To modern astronomers, it became an obstacle. Some of the universe's biggest secrets were hiding directly behind it. It was like trying to map an entire continent while an enormous mountain blocked your view. The mystery remained unsolved until astronomers realized they were asking the wrong question. Instead of trying to see through the Milky Way with visible light, why not use light our eyes could never detect? Every wavelength tells a different story. Visible light reveals stars. Infrared light passes through much of the dust. Radio waves penetrate even farther. X-rays expose the hottest regions in the universe. By combining observations from every part of the electromagnetic spectrum, astronomers slowly peeled back the curtain that had hidden the cosmos for billions of years. And what emerged was astonishing. Behind the Milky Way wasn't empty space. There were galaxies, thousands of them, then tens of thousands, clusters upon clusters stretching across unimaginable distances. Entire cosmic cities have been hidden in plain sight. Imagine discovering an entire civilization on the opposite side of a mountain that humanity had never climbed. That's how revolutionary these observations were. But one discovery stood above all the others. Near the direction our galaxy was moving, astronomers found an immense concentration of mass. It wasn't a single object. It wasn't one gigantic galaxy. Instead, it was an enormous region filled with galaxy clusters packed together far more densely than average. The amount of matter there was almost beyond comprehension. The structure became known simply as the Great Attractor. The name sounded almost mythical, as if astronomers had discovered some mysterious cosmic machine pulling galaxies across the universe. The reality was both less dramatic and somehow even more fascinating. Gravity doesn't care whether an object is visible. It only cares about mass. Every star, every planet, every black hole, every cloud of gas, every particle of dark matter contributes to the gravitational landscape of the universe. The Great Attractor wasn't pulling galaxies because it possessed some exotic force. It was pulling them because it contained an extraordinary amount of matter. Or at least, that was the first explanation. For a while, the discovery seemed to solve everything. The Milky Way's motion finally had a cause. Case closed. Except it wasn't. Because the more accurately astronomers measured galaxy motions, the stranger the picture became. Imagine following a river toward its source. You expect to find a lake. Instead, you discover the river continues beyond the lake toward an even larger ocean. That's exactly what happened. Researchers began measuring the velocities of galaxies surrounding the Great Attractor with increasing precision. If the Great Attractor were truly the destination, galaxies should slow down as they approached it. Many didn't. They kept moving, past it, beyond it, towards something even farther away. The Great Attractor suddenly looked less like the end of the journey, and more like a bend in a much larger river. That realization completely changed the investigation. Astronomers weren't simply looking for one massive object anymore. They were trying to understand the flow of the entire universe. At first glance, the universe appears chaotic. Galaxies seem scattered almost randomly across space. Some spiral, some elliptical, some collide. Others drift alone for billions of years. But zoom out far enough, and a hidden pattern begins to emerge. Imagine looking at Earth from an airplane. Roads become invisible. Cities become tiny dots. Continue climbing. Soon entire countries disappear beneath a larger pattern of continents and oceans. The universe behaves the same way. On small scales, galaxies seem isolated. On larger scales, they gather into groups. Groups merge into clusters. Clusters connect through enormous filaments stretching hundreds of millions of light years. Between those filaments lie gigantic empty regions called cosmic voids. The result is something astonishing. The observable universe resembles a gigantic three-dimensional web, a network of glowing strands woven across billions of light years. Astronomers call it the cosmic web. It's the largest known structure in existence. And once scientists realized galaxies travel along these invisible highways, the mystery of the Great Attractor became even more intriguing. Galaxies don't simply wander through empty space. They flow, just as raindrops merge into streams. Streams merge into rivers, and rivers eventually empty into the sea. Galaxies move through the cosmic web toward regions where gravity is strongest. Our galaxy is part of one of those rivers. The Milky Way isn't wandering aimlessly through the universe. It's following a gravitational current that has existed for billions of years. This completely transformed how cosmologists viewed the large-scale universe. Instead of isolated galaxies floating randomly through space, they began seeing an interconnected system. Everything influences everything else. Gravity sculpts the landscape. Dark matter forms the invisible framework. Galaxies simply follow the paths already carved by gravity over cosmic time. But there was still a problem. The Great Attractor explained part of the motion. Not all of it. Some galaxies seem to ignore the gravitational basin entirely. Others accelerated in ways that existing models struggled to explain. Then, in the early 21st century, another controversial discovery shook cosmology. Researchers studying the motions of hundreds of galaxy clusters noticed something deeply unexpected. The clusters weren't merely flowing toward the Great Attractor. Many appear to be moving together across enormous distances, almost as though an invisible current extended far beyond anything visible inside the observable universe. The phenomenon became known as the dark flow. If confirmed, it suggested something extraordinary. The gravitational influence affecting our galaxy might not even originate entirely within the observable universe. Imagine standing beside a river flowing through a valley. You assume the current is created by rain falling upstream. Then someone tells you the water actually comes from beyond the mountains, from a place nobody has ever seen. That's the unsettling implication of the dark flow. Perhaps the Great Attractor isn't the true destination. Perhaps it isn't even the biggest player. Perhaps both our galaxy and the Great Attractor itself are responding to something even larger. The idea remains controversial. Some later studies found weaker evidence for the dark flow than originally reported. Others suggested the effect might arise from limitations in the available data. But regardless of its ultimate explanation, The debate forced scientists to confront an uncomfortable truth. The universe is more interconnected than anyone imagined, and our cosmic neighborhood was much larger than we had ever realized. Then, in 2014, a remarkable discovery changed our address in the universe forever. For generations, people had memorized humanity's cosmic location: Earth, the solar system, the Milky Way galaxy, the local group. Beyond that, things became increasingly vague. Astronomers knew we belonged to the Virgo Supercluster, but new measurements revealed something astonishing. Virgo wasn't the whole story. Using the motions of more than 8,000 galaxies, scientists traced the invisible gravitational rivers flowing through nearby space. Instead of drawing boundaries based on where galaxies happen to be, they drew boundaries based on where galaxies were actually going. The result revealed something humanity had never seen before: a colossal supercluster stretching across more than 500 million light-years, containing around 100,000 galaxies, including our own. It was so vast that it deserved a new name: Laniakea, a Hawaiian word meaning immense heaven. Suddenly, our cosmic address changed. We weren't simply residents of the Virgo Supercluster. We lived inside one branch of an enormous gravitational watershed called Laniakea. Imagine discovering that the town you've lived in your entire life is actually part of a giant nation you never knew existed. Nothing physically changed, only your understanding became larger. Laniakea wasn't merely another collection of galaxies. It was a map of cosmic motion itself. Every galaxy inside, it was slowly flowing toward the same gravitational basin, toward the same mysterious region, toward the Great Attractor. At first glance, it finally seemed like the mystery had been solved. The rivers had been mapped, the destination identified, the puzzle completed. But what most people don't know is that even Laniakea may not be the final answer, because just beyond its boundaries lies one of the largest concentrations of matter in the observable universe, a structure so massive that it may be influencing the motion of everything around it. And if that's true, then the Great Attractor may not be the true attractor after all. If you could somehow step outside the observable universe, far enough that entire superclusters looked like tiny islands, you would notice something extraordinary. The cosmos isn't uniform. It isn't random. It's alive with motion. Vast rivers of galaxies stream along invisible highways, converging into gravitational basins that dwarf anything we can truly comprehend. And somewhere ahead of us, one destination stands out more than any other: the Shapley Supercluster. At first, it doesn't sound particularly intimidating. After all, astronomers have cataloged thousands of galaxy clusters. What's so special about one more? The answer lies in its sheer scale. The Shapley Supercluster is one of the most massive structures in our cosmic neighborhood, containing more than 8,000 galaxies spread across dozens of enormous galaxy clusters. Its total mass is measured in tens of millions of billions of suns. Imagine replacing every grain of sand on Earth with a galaxy. Now imagine each galaxy containing hundreds of billions of stars. Even then, the true scale of Shapley remains difficult to grasp. When astronomers first mapped it in detail, they immediately noticed something unsettling. It lies almost directly beyond the Great Attractor. That coincidence was impossible to ignore. For years, scientists had assumed the Great Attractor itself was responsible for the motion of the Milky Way. But what if they had mistaken the middle of the journey for the end? Imagine climbing a hill because someone tells you it's the highest point in the landscape. You reach the summit, only to discover an enormous mountain rising behind it. Suddenly, everything changes. The hill wasn't the destination. It was only blocking your view. This became one of the biggest debates in modern cosmology. Perhaps the Great Attractor wasn't acting alone. Perhaps much of its gravitational influence actually came from the unimaginably massive structures hidden beyond it. As researchers refined their computer simulations, something remarkable began to emerge. The motions of galaxies made much more sense when Shapley was included. The Milky Way wasn't simply falling toward the Great Attractor. Instead, both we and the Great Attractor itself appeared to be responding to an even larger gravitational landscape. The universe had become a hierarchy. Galaxies orbit stars. Galaxy groups orbit clusters. Clusters move towards superclusters. Superclusters respond to even larger structures stretching across hundreds of millions of light years. The deeper scientists looked, the less isolated anything became. Everything was connected. Everything influenced everything else. But just when astronomers thought they finally understood the cosmic map, another discovery completely overturned their expectations. Oddly enough, it wasn't another massive object that changed the story. It was something almost completely empty. Imagine hiking through mountains. You're convinced every river flows because giant peaks push water downhill. Then someone points to an enormous valley. Suddenly, you realize the rivers aren't only being pushed. They're also being pulled by the emptiness ahead. Gravity works in a surprisingly similar way. In 2017, researchers studying the large-scale motions of galaxies identified something extraordinary. A gigantic region containing almost no galaxies at all. An immense cosmic void. Yet this emptiness appeared just as important as the massive structures surrounding it. They called it the dipole repeller. The name sounds almost like science fiction, as if some mysterious force were pushing galaxies away. But that's not what was happening. Nothing was actively repelling anything. Instead, the lack of matter meant there was less gravity in that direction. Imagine standing between two magnets. One is incredibly powerful. The other is removed entirely. You naturally move toward the remaining magnet, not because the empty space pushes you, but because nothing holds you back. That's essentially what the dipole repeller represents. A vast region of missing mass. While enormous structures like Shapley pull galaxies from one side, gigantic cosmic voids allow them to drift away from the other. The result is something beautifully elegant. The motion of our galaxy isn't controlled by one mysterious object. It's shaped by the entire architecture of the universe. Mountains and valleys, peaks and basins, dense regions and empty voids. Together, they create a gravitational landscape stretching across unimaginable distances. It's less like being pulled by a single rope, and more like rolling across an endless landscape toward its lowest point. This realization transformed cosmology. The Great Attractor wasn't a monster lurking behind the Milky Way. It was part of a much larger gravitational ecosystem. But one mystery still remained. If gravity alone explains everything, why does the universe contain enough mass to create these enormous structures? When astronomers added up every visible star, every planet, every cloud of gas, every black hole, the numbers refused to work. There simply wasn't enough matter. The galaxies moved too quickly. Clusters held together far too strongly. The cosmic web itself contained more gravity than visible matter could possibly provide. Something invisible was shaping the universe. Again, the first clues appeared decades earlier. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster. He calculated how much visible matter existed inside it. Then he compared that to the speed of the galaxies orbiting within a cluster. The results were astonishing. The galaxies should have flown apart. There simply wasn't enough visible mass to keep them bound together. Zwicky proposed a radical explanation. Most of the cluster's matter couldn't be seen. At the time, almost nobody believed him. His idea sounded outrageous. Invisible matter? Matter that neither emitted nor reflected light? It seemed impossible. Yet over the following decades, observation after observation pointed toward the same conclusion. When astronomer Vera Rubin measured how stars orbit inside spiral galaxies, she discovered something equally perplexing. The outer stars were moving far too fast. According to Newton's laws, they should have slowed dramatically with distance. Instead, they continued orbiting at nearly constant speeds. It was as though every galaxy sat inside an enormous invisible halo, one far larger than the stars themselves. Today we call this mysterious substance dark matter. It doesn't glow. It doesn't absorb light. It doesn't reflect light. As far as we know, it interacts with ordinary matter almost exclusively through gravity. Yet it outweighs all the stars, planets, gas, and dust in the universe by roughly 5 to 1. Without dark matter, the cosmic web would never have formed. Galaxy clusters wouldn't exist. The Great Attractor would possess only a fraction of its current mass. The universe we know would look completely different. In a very real sense, our galaxy is falling through an invisible universe. The stars we see are merely the illuminated tips of enormous gravitational icebergs. Everything else remains hidden. Imagine walking through a city at night where only the streetlights are visible. You'd know buildings existed. You'd sense roads stretching into darkness. But most of the city would remain invisible. That's how astronomers experience the universe. The visible galaxies reveal only a tiny fraction of what's truly there. And once you realize that, the Great Attractor becomes even more mysterious. Because if most of its mass comes from dark matter, then we're being pulled primarily by something humanity has never directly observed. Something that surrounds every galaxy, every cluster, every supercluster. Something that dominates the universe, while remaining almost completely invisible. And perhaps the most unsettling question of all is this. If 95% of the universe is made of dark matter and dark energy, how can we be certain we've discovered every force shaping our cosmic journey? Maybe we haven't. Maybe the greatest attractor in the universe is still waiting to be found. For thousands of years, humanity believed the night sky was complete. Every visible star, every faint smudge of light, every constellation seemed to represent the universe itself. Today, we know something astonishing. Everything you can see, every galaxy, every nebula, every planet, accounts for less than 5% of reality. The remaining 95% is invisible. Dark matter and dark energy dominate the cosmos, shaping structures on scales almost beyond imagination, which raises an unsettling possibility. If the vast majority of the universe is hidden, what else haven't we found? The Great Attractor may seem mysterious today, but history teaches us an important lesson. Every time we've built a better telescope, the universe has become stranger, never simpler. The telescope revealed galaxies beyond the Milky Way. Radio astronomy revealed invisible galaxies hidden behind cosmic dust. Infrared observations uncovered structures buried inside the Zone of Avoidance. X-ray telescopes exposed galaxy clusters containing unimaginable amounts of superheated gas. Every technological leap peeled away another layer of reality, and every layer revealed something even larger than the last. So perhaps the greatest mystery isn't the Great Attractor itself. Perhaps it's the possibility that we're still looking at only part of the picture. Imagine standing inside an enormous cave. You shine a flashlight across the walls. Every time you move the beam farther into the darkness, the cave keeps expanding. Would you ever confidently claim you've reached the end? Probably not. That's exactly where cosmology finds itself today. We've mapped billions of galaxies. We've measured the expansion of the universe. We've discovered dark matter. We've detected gravitational waves. Yet our map remains incomplete because there are limits beyond which we simply cannot see. The observable universe stretches roughly 46 billion light years in every direction. Beyond that horizon, light has not had enough time to reach us since the Big Bang. There could be more galaxies, more superclusters, entire structures larger than anything we've ever imagined. We'll never observe them directly, not because they don't exist, but because the universe itself prevents their light from reaching us. It's one of the strangest consequences of cosmic expansion. Reality extends beyond observation. And that simple fact has inspired one of the most controversial ideas in modern cosmology. What if something beyond the observable universe is influencing what happens inside it? At first glance, the idea sounds impossible. How could something we can never see affect us? The answer lies in gravity. Gravity doesn't require visibility. It only requires mass. Imagine floating inside a dense fog. You can't see the mountains surrounding you. But if the ground slopes downward in one direction, you'll still roll. You don't need to see the mountain to feel its influence. Some researchers wondered whether the motions of enormous galaxy clusters hinted at something beyond our cosmic horizon. Could structures outside the observable universe contribute to the gravitational landscape we experience today? Most cosmologists remain cautious. Current observations don't provide enough evidence to support that conclusion. The Standard Model of cosmology successfully explains most large-scale motions using structures we already know. But the idea remains fascinating because it reminds us of something important. Observation has limits. Reality may not. As powerful as our telescopes become, there will always be a horizon we cannot cross, a place where certainty gives way to possibility. That realization changes how we think about the Great Attractor. Instead of asking, what exactly is pulling us? Perhaps the better question is, what does the Great Attractor reveal about the universe itself? Because the true importance of this mystery was never one hidden galaxy cluster. It was the discovery that the universe possesses an invisible architecture, a structure beneath everything we see. Imagine flying over a city at night. The buildings seem randomly scattered. Then the streetlights reveal a pattern. Roads, highways, bridges. Suddenly, apparent chaos transforms into order. The Great Attractor revealed something similar. Galaxies aren't randomly distributed. They're connected. The cosmic web acts almost like the nervous system of the universe. Dark matter forms invisible filaments stretching across hundreds of millions of light years. Ordinary matter falls into those filaments. Gas collects. Stars form. Galaxies emerge. Clusters assemble. Gravity shapes everything. Even our own existence depends on this hidden framework. If dark matter hadn't formed these enormous filaments shortly after the Big Bang, galaxies might never have developed. Stars like our sun might never have existed. Planets may never have formed. Life might never have appeared. The Great Attractor isn't simply a destination. It's evidence that invisible structures have guided cosmic evolution since the earliest moments of the universe. And yet, gravity isn't the only force shaping our future. While enormous concentrations of matter pull galaxies together, another force is quietly pulling everything apart. Dark energy. Unlike gravity, dark energy doesn't gather structures. It separates them. Every second, the expansion of a universe accelerates ever so slightly. Galaxy clusters drift farther apart. Superclusters slowly become isolated islands. Billions of years from now, the night sky will look completely different. Most galaxies currently visible from Earth will have disappeared beyond the cosmic horizon. Future civilizations may never know they existed. Imagine being born in a universe containing only one galaxy. No evidence of cosmic expansion. No distant galaxies. No visible Big Bang. That's likely the future awaiting any intelligent observers who exist trillions of years from now. Ironically, we live during one of the very few eras in cosmic history when a large-scale structure of the universe can still be observed. We're living at exactly the right time to discover the Great Attractor, to map Laniakea, to detect the cosmic microwave background, to understand the universe's history. Future astronomers may never have that opportunity. In many ways, we're cosmic archaeologists. The evidence is still visible, but it's slowly disappearing. The Great Attractor reminds us that the universe is dynamic, always changing, always evolving, always carrying galaxies along invisible currents toward destinations written into space-time billions of years ago. Yet perhaps the most remarkable realization isn't that our galaxy is moving. It's that we were able to discover it at all. Think about what humanity accomplished. A species that evolved on a tiny rocky planet, orbiting an ordinary star, inside one average galaxy, managed to detect its own motion through a universe nearly 100 billion light-years across, without leaving our solar system, without traveling to another galaxy, simply by observing carefully, by asking questions, by refusing to accept easy answers. Science didn't reveal the Great Attractor because someone stumbled upon it. It revealed itself through patience. Decades of observations, thousands of astronomers, millions of measurements, each discovery building upon the last. The universe rarely gives away its secrets easily, but when it does, they're often more extraordinary than anyone imagined. And perhaps that's the greatest lesson hidden inside this mystery. Every answer opens the door to an even bigger question. The Milky Way led us to galaxy clusters. Galaxy clusters led us to superclusters. Superclusters led us to the cosmic web. The cosmic web led us to dark matter. Dark matter led us toward entirely new questions about the nature of reality itself. The deeper we look, the larger the universe becomes. And somewhere beyond the edge of everything we've mapped, the next mystery is already waiting. Imagine, for a moment, that you could freeze time. The stars stop shining. Galaxies stop moving. Gravity itself becomes visible. What would the universe actually look like? It certainly wouldn't resemble the beautiful pictures captured by the Hubble Space Telescope or the James Webb Space Telescope. Those breathtaking images tell only part of the story. They show us light. But gravity doesn't care about light. Gravity sees everything. It sees the enormous halos of dark matter surrounding every galaxy. It sees invisible bridges connecting galaxy clusters. It sees vast valleys stretching across hundreds of millions of light years. If your eyes could somehow detect gravity instead of light, the universe would appear almost unrecognizable. The stars would become tiny decorations floating inside colossal invisible mountains of dark matter. Galaxy clusters would resemble glowing islands sitting atop gigantic gravitational peaks. And the Great Attractor wouldn't look like a mysterious object. It would look like one of countless low points in an unimaginably vast gravitational landscape. That realization changes everything. For decades, The Great Attractor was presented as one enormous cosmic destination. Today, astronomers see something much more elegant. The universe isn't being controlled by a single monster hidden behind the Milky Way. It's behaving exactly the way rivers behave on Earth. Water doesn't flow because one lake pulls every river toward it. Water follows the shape of the land. Gravity works the same way. The cosmic web is the landscape. Dark matter forms the mountains and valleys. Galaxies simply follow the paths created billions of years ago. Our galaxy is not choosing a direction. It is following the geometry of the universe itself. And that may be one of the most beautiful ideas in modern science, because it means that what once looked like chaos is actually order on the largest scale imaginable. The Milky Way's journey began almost 14 billion years ago, long before the Earth existed, long before the Sun formed, long before our galaxy even looked the way it does today. Tiny fluctuations in the infant universe were stretched across space during the earliest moments after the Big Bang. Those tiny differences in density became slightly stronger under gravity. Over millions of years, they attracted more matter, then even more. Eventually, they became the invisible dark matter scaffolding upon which galaxies would later grow. Without those tiny fluctuations, there would be no Milky Way, no stars, no planets, no life, no observers wondering why galaxies move. The Great Attractor isn't merely affecting our future. Its story began before our galaxy was even born. And in a way, so did ours. If we could somehow rewind cosmic history like a movie, we'd watch the universe transform from a nearly uniform sea of particles into a magnificent network of glowing galaxies. The process wouldn't look random. It would resemble frost spreading across a window, or lightning branching through the sky. Simple rules creating astonishing complexity. Again and again, across billions of light years. Every galaxy, every cluster, every supercluster, connected, every one of them participating in a cosmic dance that has continued for nearly the entire history of existence. The more scientists map these structures, the more one conclusion becomes impossible to ignore. The universe is not a collection of isolated objects. It is a connected system. The Milky Way is connected to Andromeda. The local group belongs to Laniakea. Laniakea interacts with neighboring superclusters. Those superclusters influence even larger structures. Everything affects everything else. Perhaps that's the most profound lesson the Great Attractor has taught us. Nothing exists alone. Not stars, not galaxies, not even entire superclusters. Everything belongs to something larger. And every discovery has made our place in the universe simultaneously smaller and more meaningful. When humanity first looked into the sky, we believed Earth was the center of everything. Then we discovered the solar system, then the Milky Way, then billions of galaxies, then the cosmic web. Each discovery removed us from the center. Yet strangely, each discovery also made us more connected to the universe than ever before. We are not separate from the cosmos. We are participants in its evolution. The iron in your blood was forged inside ancient stars. The calcium in your bones was created during stellar explosions. The oxygen you breathe once drifted through interstellar clouds long before Earth existed. Even the atoms making up your body have traveled through galaxies for billions of years before becoming part of you. In the deepest sense, you are already part of the Great Attractor story. Every atom in your body has experienced the same cosmic history as the Milky Way itself. That's one of the most astonishing consequences of modern astronomy. The line between us and the universe begins to disappear. We are not observers standing outside reality. We are one of its countless expressions. And perhaps that's why mysteries like the Great Attractor continue to fascinate us. They're not simply questions about distant galaxies. They're questions about our own origins, our own future, our own place in an unimaginably vast universe. But despite everything we've learned, the mystery isn't over. Far from it. New telescopes are already beginning another revolution. The Vera-C Rubin Observatory will map billions of galaxies with unprecedented precision. The Euclid Space Telescope is creating the most detailed three-dimensional map of dark matter ever attempted. The Nancy Grace Roman Space Telescope will explore enormous regions of the universe with extraordinary sensitivity. Future radio observatories like the Square Kilometer Array will reveal structures invisible to every previous generation of astronomers. Each new mission promises another leap forward. Perhaps they'll finally explain every motion inside Laniakea. Perhaps they'll discover entirely new superclusters. Perhaps they'll reveal unexpected properties of dark matter. Or perhaps they'll uncover another mystery even stranger than the Great Attractor. History suggests that's the most likely outcome, because every time humanity believes we've reached the edge of knowledge, the universe quietly reminds us how much remains unseen. The Great Attractor was never the end of the story. It was the beginning of a much larger one, a story about invisible matter, invisible structures, invisible currents flowing across the largest scales imaginable. A story that transformed astronomy forever. And maybe that's the greatest scientific lesson of all. The universe is under no obligation to match our intuition. Reality is stranger than common sense, stranger than imagination. Sometimes the biggest discoveries aren't the objects we find. They're the assumptions we leave behind. The Great Attractor forced astronomers to abandon one of the oldest assumptions in science, that what we see is all there is. Today we know better. The visible universe is only a thin layer covering a much deeper reality. Most of the cosmos is hidden. Most of its gravity is invisible. Most of its future remains unwritten. And somewhere beyond every map we've created, beyond every supercluster we've cataloged, beyond every observation we've made, new mysteries are already waiting. Perhaps one day, future astronomers will look back at our understanding of the Great Attractor the same way we look back at ancient maps of Earth. Remarkably accurate for their time, yet missing entire continents. That's the beauty of science. It never truly ends. Every answer becomes the beginning of another question. Every discovery expands the horizon. Every mystery invites another generation to look a little farther. So the next time you step outside on a clear night, look toward the stars. Remember that our entire galaxy, every star in the Milky Way, our sun, the Earth beneath your feet, and even you, are traveling together through an invisible landscape sculpted by gravity over nearly 14 billion years. We're passengers on a journey that began long before humanity existed. A journey through rivers of galaxies, across an invisible cosmic web, toward destinations we are only beginning to understand. The universe is moving, and so are we. Not randomly, not aimlessly, but as part of something far larger than ourselves. And perhaps that's the most extraordinary realization of all. The greatest mysteries in the universe aren't waiting at the edge of space. They're already carrying us toward them. If you enjoyed this journey through one of the greatest mysteries in modern astronomy, don't forget to subscribe and join us for more explorations into the universe, black holes, dark matter, cosmology, and the biggest unanswered questions in science. Because the more we discover, the more incredible reality becomes. And until our next journey through the cosmos, keep looking up.